In this example, we're going to try to find the point on this given plane that's closest to the point 1, 1, 1. And there's more than one way to do this, but we're going to try it by using Lagrange multipliers. So to use Lagrange multipliers, we need to first come up with a function that we're trying to optimize. In this problem, we can see we're trying to minimize the distance between the plane and the point. So the distance function is a good place to start. Let's remind ourselves of the distance between a point, 1, 1, 1, and another point, x, y, z. You recall that's given by this. But we not only want to minimize the distance between a point and 1, 1, 1, but we need the point, x, y, z, to remain on the plane. So that's going to be our constraint. So we have a function we're trying to minimize, and we have a constraint, which is going to lead naturally to a Lagrange multiplier setup. Before we continue, instead of using this distance function as it is, I want to point out a little trick. It's often easier to use the distance squared function, and this will work because it will have a minimum value at the same point as the distance function. So we're going to end up getting the same point, but it'll just be a little bit easier algebraically. So if we instead use distance squared as our function, on the next board, let's define that as our function f. And then we have this constraint that we need to be on the plane. So I'm rewriting the equation of the plane, setting everything to 0, and then defining this function g. And this is to help us in our setup for Lagrange multipliers. So now recall, once we have the function and the constraint, we know that the gradients of both f and g must be scalar multiples of each other. And then in addition, we must be on the plane, so we need g to be equal to 0, staying on the plane. So I want you to go ahead and put this on pause, find the gradients of both of these functions, and then use it to set up a system of equations. Okay, so the first part, if we find the gradient of f and the gradient of g, we'll get this. In order for these vectors to be scalar multiples of each other, we have to look at them component-wise. So this means that the I component of f, which is just 2 times x minus 1, that's got to be equal to lambda, my scalar multiplier, times the I component of g, which is just 1. Well, I can do this with also the j and the k components. And that'll get me my first 3 equations, and the last equation is just that I still need to be on the plane. So this is now my system of 4 equations and 4 unknowns, and this is what we're going to try to solve. We know that the method of Lagrange multipliers tells us that if there is an absolute minimum that satisfies this criteria, then we will find it using this method. Recall that not all of the points that you find will necessarily be a minimum or a max, but if there is a min or a max that exists, it will be in the set of points that you find. So let's move to a new board just to set this up. Okay, and again, there's more than one way to solve these systems of equations. I generally like to start by trying to eliminate lambda from the first 3 equations, so I do that by trying to solve for lambda in each of these equations. So if we do that here, the top equation's already solved for, lambda's already by itself. But the next 2, we can go ahead and get lambda by itself. And then we're going to need all 3 of these equations up here to equal one another. So let's write that out. Need lambda to equal each other. Just save this. Okay, there, I was getting ahead of myself for a second. Okay, so now let's go ahead and look at these first 2 equations, so right here. In other words, I'm just looking right here. And in these, we can now solve this equation set here either for x or y. It doesn't matter which one you pick. I'm going to solve it for x. When we solve this for x, we're going to get that x is equal to 1/2 y plus 1/2. And now we're going to look back up here. Now we're going to look at these 2 equations, or in other words, We write that here as this one equation, and that's going to be, put a little line here. So now I'm trying to solve y minus 1 is equal to 2/3 z minus 1. And again, I can solve this for either y or z, but the trick here is going to be to pick whatever variable you solve things in terms of in the first equation. So we solve things in terms of y, got x by itself. We're going to want to do the same thing here. We're going to want to solve things in terms of y, so we're going to get z by itself here. So we're going to get z is 3/2 y minus 1/2. Okay, so far we've just used the top three equations, and now we need to go back to our constraint, this bottom equation, and plug everything into there. So the constraint is x plus 2y plus 3z minus 13 is 0. So we know that x is 1/2 y plus 1/2, and then we're going to have plus 2y, and then plus 3 times z. So now everything is just in terms of one variable. So if you've done this right, by this step you should be able to solve completely for one of the variables. And we see that if we simplify, expand this out a little bit, we're going to get that 7y is equal to 14. So this tells us that y has to be 2. And once we know y, then we can get x and z, because x is 1/2 y plus 1/2. So this tells us that x is going to have to be 3/2, and z is going to have to be 5/2. So this just gives us 1 point. This tells us that we actually only have 1 point for the solution to this system of equations. And we can conclude that this point will give us the minimum distance between the point 1, 1, 1 and the plane, because we know a minimum must exist between the point 1, 1, 1 and the plane, and the distance to the plane. We know an absolute maximum won't exist, so there won't be some point on the plane in which the distance between that point and the point 1, 1, 1 will be an absolute max, because the plane is infinite. So you can always continue to get further and further away on the plane from the point 1, 1, 1, which means the only solution that we could find here is the absolute minimum. And we can go a little bit further and find out what that minimum distance is. So recall, let's go back to our original function. And wait, actually before I go to that, let me just summarize what I just said. Okay, now so let's find the actual distance, minimum distance between the point and the plane. So our function was the distance squared, so if we evaluate the function at the point, we're going to get 14/4, or 7/2, which tells us that the actual distance is just going to be the square root of that. Okay, and again, that's the minimum distance between the point 1, 1, 1 and the plane. And that's it.